Hi there, welcome to my channel. In this video, I'm going to discuss about the solution for finding maximum depth of a binary tree. Let's look at the problem description. We are given the root of a binary tree and we have to return its maximum depth. A binary tree's maximum depth is the number of nodes along the longest path from the root node down to the furthest leaf node. So in the example 1, so the depth is 3 because 15 and 7 are the furthest leaf node. Okay, so the number of nodes in that path is 1, 2, 3. So that's why the output is 3. So in the case of example 2, so this tree is 1 is the root node and the 2 is the left child. So the number of nodes in the longest path is 2, node 1 and 2. So that's why the output is 2. So the constraint for this problem are the number of nodes in the tree is in the range from 0 to 10,000 and the node value is ranging from -100 to 100. Let's look at the approach to solve this problem. We are given this tree 3, 9, 20, 15, 7 and the depth of this tree is 3. So the longest path has 3 nodes. Okay. How we can compute the maximum depth? Basically we can compute the depth in a bottom up way. First we compute the depth of the leaf node, then its parent node, then all the way to the root node. And finally we can return the computed depth. This requires the processing of children nodes first and then parent. Which traversal we can use? Post order traversal. So in that we always process the left and right child first and then we process the parent node, right? So we can do post order traversal on this tree and compute the depth. Depth of the tree with the single node is 1. There are few cases we need to consider. The first one is the node being processed do not have any children. Okay, so in this case the depth is 1 and then the node being processed has only left subtree. Okay, so in this case the depth of this tree is 1 plus the depth of the left child, and then for this case where the current node has only the right subtree, in this case the depth of this tree is 1 plus the depth of the right subtree. And the fourth case is the node being processed has both left and right child. In this case we have to compare the depth of the left subtree and the right subtree. Whichever is maximum we have to add that to 1. So in this case the left subtree is deeper, so we have to add the depth of this subtree plus 1 as the depth of this entire tree. In this case the right subtree is deeper, we have to add the depth of this subtree and plus 1. That's what I have written here. First we initialize the myDepth variable to 1, then we check whether the current node is null. In that case we have to return depth as 0 because empty tree's depth is 0. And next we check is whether the current node do not have any children. In that case we have to return the myDepth which is 1. Next we initialize the left depth to 0 and right depth to 0. Then we check whether the current node has a left child. If that is true, then we make a recursive call to max depth function with the left child and assign the return value to left depth variable. And if the current node has a right child, then again we make a recursive call to process that right subtree and assign the return value to right depth. Then we check whether the left depth computed is equal to 0. In that case we add the right depth to myDepth variable, and if the right depth is 0 then add the left depth to myDepth variable. If both the variables are not equal to 0, then we have to compare which is greater and add that value to the myDepth variable. So if the left depth is greater than the right depth, then we have to add the left depth to myDepth. Otherwise, we have to add the right depth to myDepth. Finally, we return the myDepth. Let's look at the flowchart. Input for this procedure is root. First, we initialize the myDepth to 1. Then we check whether the current node is null. If that is true, we have to return 0 as the depth. Otherwise, we check whether the current node has children. If it doesn't have any children, then we have to return the myDepth, which is 1. The single node depth is 1. Otherwise, we initialize the left depth and the right depth variable to 0. Then if the current node has the left child, then we make a recursive call to max depth to process the left child and assign the return value to left depth. And next, if the current node has right child, then we have to make a recursive call to process the right child and assign the return value to right depth. So once the left and right depth are computed, then we have to check whether the left depth is equal to 0. If that is true, then add the right depth value to myDepth. If the right depth is equal to 0, then add the left depth value to myDepth. If both are not equal to 0, then we have to compare which is greater. So in this case, if left depth is greater than the right depth, then add the left depth to myDepth. Otherwise, add right depth to myDepth. Then finally return the myDepth. Let's move on to coding. First, I initialize the myDepth variable to 1. And then I check whether the root node is null. If it is true, I return 0. Else, if the current node is the leaf node, then return the myDepth. Next, I initialize the LDepth and RDepth variable to 0. And then I check if the current node has a left child, then I make a recursive call to process that left subtree. And assign the return value to LDepth variable. And then if the node has a right child, then I make a recursive call to process that right subtree. And assign the return value to RDepth variable. Next, I check whether the LDepth is equal to 0. If it is true, then I add the RDepth value to the myDepth variable. Else, if RDepth is equal to 0, then I add the LDepth value to myDepth variable. If both LDepth and RDepth are not equal to 0, then I check whether LDepth is greater than RDepth. If this is true, then I add the LDepth value to myDepth. else I add the rdepth value to myDepth variable. Finally, I return the myDepth. Next, I am going to run the test cases. All the tests passed. Next, I am going to submit this program. Cool, this program is accepted. Next, I am going to do the code walkthrough with sample input. We are given the root of the binary tree, which has 5 elements, and the expected output is 3. Okay, so for this tree, the longest path has 3 nodes, so that's why the expected output is 3. Okay, so first we initialize the myDepth variable to 1. Okay, and now we are processing the root node. First we check the root is null and it is false, and then we check whether the current node do not have any children. In this case it has both left and right child, so we go ahead and initialize the left depth and the right depth variable to 0. Okay, then we check whether the current node has a left child. In this case it has 9, so we make a recursive call to process that subtree. So when we enter this function, the root points to node 9 and the myDepth variable is initialized to 1, and this node is not null, but this node do not have any children, so we simply return the myDepth value back to the caller. Okay, so when we leave this function, the myDepth is same 1. Okay, and when we come back, we check whether the node has a right child. The node 3 has a right child, so in this case 20. So we make a recursive call to process this subtree. Okay, okay, so once we come here, we initialize the myDepth variable to 1, and then the left depth and the right depth to 0, and then we check whether this node has left child. It has 15, so we make a recursive call to process that left child. So when we enter this function, root points to 15, we initialize the myDepth variable to 1. We check whether this node do not have any children. In this case it is true, this is a leaf node, so we return myDepth, return 1 back to its parent. Next we check whether the node 20 has right child. In this case it has 7, so we make a recursive call to process the right child. So here we are processing the right child. So here also this node is not null, but this is a leaf node, so we simply return 1 as the depth of this node. So both the left child and the right child had returned 1 as the depth, so both returned 1 as the depth. Okay, so once we come here, we check whether the left depth is equal to 0. It is not, and right depth is also not 0, and then we compare. Because both are equal, we add the right depth to myDepth. So myDepth is already 1 plus the right depth is 1, so the myDepth becomes 2. And then when we return, so when the control returns back to the node 3, this subtree returns the depth as 2, and this one returns 1 as the depth of the left subtree. So again when we compare, we have to add the larger value. So in this case we add the rdepth to the myDepth variable. MyDepth is already initialized to 1, so 2 plus 1, 3. So 3 is returned as the depth of the given input tree. That is an expected output. Next I am going to do the time and space complexity analysis for this solution. The time complexity for this solution is order of n. So in order to compute the depth of the tree, we have to process all the nodes in the tree. So in the post order traversal, we visit all the nodes and process them only once. Okay, so in this case there are 5 nodes, so we have to visit all the 5 nodes. So if there are n nodes, we have to visit all the n nodes, so that's why time complexity is order of n. Space complexity is also order of n because we compute the depth recursively. So when we make a a recursive function call. Internally we use the system stack space. So if the tree is fully balanced, then the maximum number of active frames will be log n, where n is the number of nodes in the tree. Okay, but if the tree is skewed binary tree, in that case the number of frames in the call stack will be n. So the space complexity is order of n. Thanks for watching this video. Have a great day.